You ever step into an elevator and just not think twice? Of course you do. We all trust it to be safe, smooth, and just work. But behind that calm, quiet ride, there's a hidden battle of forces constantly at play. Today, we're going to pull back the curtain on one of the most critical, yet almost invisible, factors in elevator engineering. So let's get right into it.
It really all boils down to this one question. There is a single, silent force that, if it's not managed perfectly, acts like a hidden saboteur inside the system. It dictates how fast parts wear out, how reliable the elevator is, and, ultimately, how safe you are. So what is this invisible force?
Well, the culprit is something engineers call specific pressure. Now, I know that might sound super technical and maybe a little boring, but I promise you it is the absolute key to understanding the health, the safety, and the longevity of any traction elevator. So what exactly is it? Okay, imagine the entire weight of the elevator car, plus everyone in it, being supported by those steel ropes. Now, picture all of that force getting focused on the tiny, tiny little area where the rope touches the pulley that moves it. Specific pressure is just the measurement of that incredibly concentrated force. To really get it, think of a thumbtack. The normal force is how hard you push on the tack. The contact area is that tiny, sharp point. A little push on a tiny point creates a ton of pressure, right? It's the exact same idea here. You've got the force pushing the rope down into its groove, divided by the very small surface area where they're actually touching.
And of course, engineers need to measure this precisely. They do it in newtons per square millimeter, which, by the way, is the same thing as a megapascal. This lets them calculate and control this critical force with incredible accuracy.
So, this brings us to the real challenge for engineers. Managing specific pressure is this incredibly delicate balancing act. You need enough of it to create friction so the ropes grip and don't slip, but not so much that you're literally grinding the entire system into dust. So how do they control it? Well, it turns out the number one most important factor, the thing engineers can design and control from the very beginning, is the physical shape of the groove that the rope sits in. It all comes down to geometry. First up, you've got the U-groove. You can think of this one like a gentle cradle or a little hammock for the rope. Its wide, rounded shape creates a really large contact area, which spreads that force out. And the result? Lower specific pressure and way less wear and tear on the rope. This is why it's the go-to choice for almost all modern, high-speed elevators where you want those ropes to last a long, long time. And then you have the V-groove. This shape is all about one thing: grip. That sharp V shape literally wedges the rope into place, which dramatically increases the force and gives you maximum traction. But what's the catch? Well, that wedge effect creates a tiny contact area and sky-high specific pressure, which means everything wears out much, much faster. And this table just lays it all out perfectly. U-grooves mean a big contact area, low pressure and low wear. They're all about durability. V-grooves are the opposite, small contact area, high pressure, high wear. They're all about raw traction. This is why you really only see V-grooves in older systems that needed that extra gripping power, while modern elevators have pretty much all moved to some version of the U-groove. But of course, it's not just about the groove shape. It's a really complex puzzle. Obviously, the more weight in the car, the higher the rope tension and the higher the pressure. Using thicker ropes can help spread that load out. Even things like the hardness of the steel and the exact right amount of lubrication play a huge part. All right, so we get what specific pressure is and what affects it, but what actually happens when it's too high? What are the real-world stakes? Well, this is where things get pretty serious because it kicks off a disastrous chain of failure. This quote just nails it. It's not a single problem. You can think of excessive specific pressure as the first domino to fall. It triggers this cascade of issues that can compromise the safety and integrity of the entire elevator system. And here's what that chain reaction looks like. It starts with high pressure. That causes the rope and the groove to wear down at an alarming rate. As they wear out and change shape, you start to lose traction. With less traction, the risk of the rope slipping goes way up. And in a worst-case scenario, that can lead to a total loss of control. It's a truly vicious cycle. And the physical damage just spreads through the system. Ropes get worn out way too early and risk breaking. The sheave grooves themselves get deformed and need a really expensive replacement. The motors and bearings are put under enormous strain. And for you, the passenger? The ride gets noisy, shaky, and just plain uncomfortable.
It's a total system-wide breakdown.
Okay, enough doom and gloom. That was the problem. Now, let's talk about the solution. The good news is that engineers have a really comprehensive blueprint for managing this force and turning what could be a disaster into a model of safety and durability. It all starts right at the beginning, on the drawing board. It's about making smart choices, like picking the right groove type for the job, or spreading the load across more ropes instead of just a few. It means using high-quality, wear-resistant materials and making sure every single component is aligned with microscopic precision. But, a brilliant design is only half the story. Proactive, relentless maintenance is just as crucial. We're talking about regular physical inspections with special tools to measure wear, and also using advanced tech like thermal imaging and vibration analysis to spot hidden stresses long before they become big, dangerous problems. And none of this is just guesswork. Engineers and technicians are guided by really strict international standards, like EN 81 in Europe or ASME A17.1 in North America. These safety codes provide the rule book, setting the minimum requirements for everything from materials to safety factors, all of which help manage specific pressure. Technology also plays a massive role here. Modern electronic systems called VVF drives allow for incredibly smooth starts and stops. You know that gentle feeling when a new elevator starts moving? That's what this is. It gets rid of the sudden jerks that cause those damaging spikes in pressure, keeping the forces on the ropes nice and steady. So, the big takeaway here is that there's no single magic fix. It's about a complete, holistic approach that combines smart design, proactive maintenance, global standards, and modern technology. That's how expert companies like Novin Pooya Elevator, who provided the research for this explainer, make sure the systems they build are fundamentally safe and built to last. Which brings us right back to where we started. Every single time you step into an elevator, you are placing your trust in this incredibly complex system. And now you know that a huge piece of earning that trust comes down to managing this one hidden, powerful force. It makes you wonder, doesn't it? Are the hidden stresses being managed in the elevators you ride every day?